Hello everyone, welcome to another episode of Coding Adventures. Today we're back to chess. So what I'd like to do is take this little chess playing program that we made about 2 or 3 years ago now, and figure out how good it actually is. My plan for doing that is to simply let it loose on a popular chess website called Lichess, as a registered bot account of course, and see what sort of rating it ends up with. Before we do that though, I can't resist trying to make it just a little bit stronger so that it's hopefully able to put up a good fight. Now, to test whether the changes we make are actually helpful or not, I've started by making a little program called the Match Manager. And the idea is that we'll be able to connect up 2 different versions of our chess program, so we can have the new version battle the old version, to make sure we haven't accidentally made it worse. They need to play a wide variety of positions for it to be a good test though, so I'd like to start each game from a random position. To get some random test positions, I've gone over to the Lichess database to first download a bunch of games. Wait a minute, this is 35 gigabytes for 1 month of games. That's too much chess. Let's go back in time to something a bit more manageable. Okay, 500 megabytes I can work with. So we now have this file of 2.5 million games in the portable game notation format, and I like that it also includes the name of the opening, because if we choose games that started with different openings, that should ensure some more variety in our test set. Okay, I've just finished struggling to write some simple Python code for a change, because I wanted to use this nice library to extract random positions from the games, where there are still lots of pieces left to avoid any totally boring positions. Running this took a couple of minutes to finish, but if we just fast forward time, we now have a list of positions in the Fen notation that we talked about last video. But I only want positions that are roughly equal for our test set, so with some help from the internet, I've managed to get some code working that automatically feeds each position into Stockfish, one of the strongest chess programs in existence, to filter out all the ones that are unfair to either side. With that done, I'm going to try running a full match between 2 copies of version 1, just to make sure that everything goes smoothly. They're playing 500 different positions, both as black and white, so 1,000 games in total, with a generous thinking time of 100 milliseconds per move. This will probably take a few hours to run, so feel free to have a nap, and I'll wake you up when it's done. You won't be shocked to learn that it was a pretty even match between version 1 and version 1, with the one version 1 winning 347 games and losing 355. So with our test setup working, let's try to actually improve the program. I'd say there are 2 main areas we can focus on, search and evaluation. And let's start with search, because while that test was running, I've been looking back at some of this old code, and I noticed something nice and easy that we can begin with. So we're doing something here called iterative deepening, which is a fancy name for just first searching 1 move ahead, then if the search hasn't been cancelled yet, we increase that to search 2 moves ahead, and so on. And that way, no matter when the search is cancelled, we'll always have the move from the previous iteration ready to play. At least that's what I thought when I wrote this. I thought that once the search is cancelled, we just have to throw away all the work from the current unfinished iteration, because how could we trust what it says is the best move when it hasn't looked at all the possible moves yet? But that's a bit silly, because so long as we begin each new search by looking at the best move from the previous iteration, then say the search is cancelled halfway through, either it will still think that's the best move, in which case no harm done, or it will have found a better move, which we should obviously take. So I'll change things around a bit here so that it accepts the new result even if that search iteration was incomplete, and then in the giant mess that is the main search function, I'll just make sure that when we're choosing the order in which we're looking at the moves, we guarantee that the best move from the previous iteration comes first. Okay, so let's just play a few moves to make sure I haven't broken anything. Okay, it looks like I've broken something. It wants to make the move a1 to a1, which is definitely not allowed. That's actually how I represent a null move, because to try and be efficient with memory during the search, I've packed all the information about a move into a 16-bit value, with the first 6 bits giving the index of the start square, the next 6 giving the index of the target square, and the last 4 bits being a flag for things like promotions and so on. So an invalid or null move, which I've just assigned the value 0, tells us to move from square 0 to square 0, which is A1 to A1. So I guess the problem arises if the search iteration is cancelled before it can even finish looking at the first move, meaning we just need to add a little null check over here. Alright, with that fixed, I've set up a match, and let's see how it goes. Okay, the results are in for version 2 versus version 1, and we have 141 wins to 836 losses. Clearly, I've made a huge mistake. I have no idea what it is though, so I've started by looking at some of the games it played, and it is making catastrophic blunders like playing queen b6 in this position, where it can of course just be captured by the bishop. Delving into the search logs, we can see it begins by wanting to play the far more sensible knight f6, and this remains its top choice through all the iterations where it thinks it's a little bit worse, until the search is cancelled when it suddenly thinks the position is dead equal and blunders the queen instead. Okay, this has led to me discovering a really sloppy mistake in my old code, which is that when the search is cancelled, it returns 0 immediately at the top of the function, which is fine, but what evidently slipped past me's mind is that this is a recursive function, so that's not the end of the story. That 0 is going to show up as the evaluation over here, so if it thought the position was worse before, suddenly it sees, wow, I can get an equal position by making whatever random move the search happened to be cancelled on. The only reason this wasn't wreaking havoc before is that I was wastefully discarding the results from the unfinished search, but now that we are using those results, we can just add another exit point here so that we do actually quit the search immediately. Alright, running the test match again with this fix gives us a score of 409 wins to 270 losses, which is much more encouraging. Something I realized while this was running though is that before we fixed the search to actually exit immediately when cancelled, those faulty evaluations would have been stored in the transposition table, which is just a giant lookup table we use to avoid constantly re-evaluating positions that we've come across already. So up here where we were starting the search, I had originally left this bewildered comment about having to completely clear the transposition table before each new search, to ward off mysterious blunders. I guess now we know why. I am very excited to delete this horrible little line of code, and now with the stored evaluations persisting across moves, the search should be a lot more efficient. So let's run a test against our previous version. Alright, this has come back with 399 wins to 387 losses, which is very underwhelming. I really expected that to make a bigger difference. Okay, I've been investigating a bit because I was confused by that result, and what I'm seeing is that the transposition table is getting filled up suspiciously quickly, meaning it very soon has to start overwriting old positions. The reason it's suspicious is that I'm using a gigantic 1 GB table, and there's no way it should be filling up that fast. Okay, my face is starting to hurt from all the face palming I'm doing today. I have some code for reporting the size of the transposition table, and it does this by first figuring out the size of each entry in bytes, which it then multiplies by the number of entries, divides by 1000 and says that's the size in megabytes. This dodgy maths means that the table wasn't a whole gigabyte like I thought, but actually just about 1 megabyte. While we're here fixing this, let's actually quickly change this calculation around so that instead of specifying the number of entries we want, we'll calculate the number of entries based on the desired size in megabytes, because that's a much more intuitive setting. And let's maybe set it to a modest 64, because that seems nice and thematic. I'll then try this out again on the same position, and we can see that it's filling up a lot more slowly now. So I'll run the match once more with the new 64 megabyte table, and this time we get 386 wins to 246 losses. So a fairly significant upgrade. Now, I think always testing against the most recent version is a good way to judge if the program has improved, but to keep track of our overall progress, I also want to keep a record of how each version compares to the original version 1. So far we have version 1 against itself, not terribly interesting, Then there's version 2, which no longer wastes the result of incomplete searches. And now we can add our latest build with the fixes to the transposition table, and against version 1, that is scoring 484 wins to 218 losses. Alright, now I've been spending a bit of time doing some research, trawling through various discussions and heated arguments on old chess programming forums, trying to find the specific version of an archive of a site where the link to the article I want to read actually works, and of course going down the incredible rabbit hole that is the chess programming wiki, where one moment you're reading a mundane article about the names of different types of nodes in a search tree, and the next you blink and suddenly it's dark outside and you find you're consulting a chart about the movement of knights and how that relates to the orbital period of Mercury, and you ask yourself, how did I get here? Suffice it to say, I have plenty of new ideas to try now. One of these is a technique called search extensions. So at the moment we look equally deeply into all moves, but it'd probably be wise to pay special attention to the most potentially interesting ones. For example, we could say that if the current move puts the opponent in check, then we'll extend the search to go one move deeper. Just to prevent things from potentially getting out of hand though, I'll set an arbitrary limit on how deep these extensions can actually take us. Alright, I've tested this in a match against our previous build, and it scored 433 wins to 237 losses, which is a really nice improvement for such a simple idea. I also tested it against version 1 for interest's sake, where it scored 561 wins to 169 losses, so we're seeing some pretty consistent progress so far, and hopefully it's going to stay that way. Okay, I've just quickly separated out the extension logic to its own tiny function, because things were getting quite cluttered, but it's doing the same thing as before. So now let's try extending the search for other types of moves as well. For example, if a pawn is on the verge of promoting, we should probably keep searching to find out whether that's going to be successful or not. So let's find out what type of piece was moved, and also what rank it was moved to, and then we can just write a little if statement that says if we've just moved a pawn and it's now on the 7th rank, so index 6, or the 2nd rank, which is index 1, then we'll want to extend the search by one move. And let's see if this extension also makes such a big difference. It made a big difference, alright. We're now getting 107 wins to 610 losses. That's very unfortunate. Okay, I was about to delete this code when I realized I've actually blundered my brackets here. The problem is just that AND has a higher precedence than OR, so we're not actually testing if a pawn has reached either the 7th or the 2nd rank, but rather if a pawn has reached the 7th rank, or something has just moved to the 2nd rank. So that means we're extending loads of totally uninteresting moves and wasting an enormous amount of precious search time. So let me fix that quickly and run the match again. Okay, this time the score has ended up at 337 wins to 273 losses. Not nearly as big a difference as the check extension, but definitely helping out a little. As always, I'll also test this against version 1, but it actually doesn't seem to be doing any better than the previous build there, which is a bit surprising to me, but I guess it makes sense that improving against one opponent doesn't necessarily guarantee that you'll play better against a different opponent. Anyway, I've been experimenting with a few other extensions behind the scenes, such as extending if a pawn actually manages to promote to a queen, and also extending when a player has only one legal move available. But these didn't seem to help the program at all, so I'll leave them out. While all these tests have been running, I've mainly just been going through and refactoring all the code since I left it in quite a mess last time. There's nothing exciting to show from all this, of course. Everything should behave exactly the same as before. Except that's not how chess works. What have I done? Okay, this first move advantage is getting out of hand. Fortunately, I was able to enlist the help of a professional bug hunter, who was very helpful in fixing the problem. Alright, so with the code tidied up and everything behaving again, let's get back to making the engine stronger. We've spent a bit of time improving the search already, so let's work on the evaluation a bit for a change. At the moment, our evaluation function considers just three simple terms: The first of these is the amount of pieces on the board. So it adds up the number of pawns multiplied by the value of a pawn, plus the number of knights multiplied by the value of a knight, and so on. And of course, these are just very generalized estimates of what each piece is worth. The second term takes into account where on the board each piece is located. So for example, these are the square scores for knights, meaning that knights on more central squares will be valued more highly, since they're able to control more squares. Finally, the third term is this mop-up score. Basically, when we have an advantage in the endgame, we want to encourage the king to move closer to the enemy king, to help push it to the edge of the board where it's easier to deliver checkmate. Here's an example of that term in action. Now, I think the program plays surprisingly well for having such a limited understanding of the game, but let's try giving it some extra knowledge to work with. To begin with, let's take a look at those square scores again, this time for the king. We can see that these scores are simply encouraging the king to find shelter on either edge of the board, and discouraging him from charging into enemy territory, because he's not a very good fighter. Once the dust of the opening and middle game has settled though, and we move into the endgame phase with not so many scary pieces left on the board, the king should stop cowering in a corner, and start thinking about being useful for once in his life by supporting the advancement of the friendly pawns, or getting in the way of the enemy pawns. So I have a second table of king square scores here to entice the king to move more towards the center of the board, and we can just blend between these two tables based on the number of remaining enemy pieces. I actually started implementing this last episode already, but ended up leaving it out because I felt like the king was being a bit too aggressive, and I didn't have the energy to tweak and test it. Now that we have this nice little testing framework though, we can just let the match run and see how it goes. Okay, the results are in, and the side with the aggressive king has ended up with 385 wins to 276 losses. Not bad, and playing against version 1, it's now scoring 630 wins to 137 losses. That was pretty effective, so let's try doing a similar thing for the pawns. Currently, they're being encouraged to move up the board to become queens, but we also have this conflicting goal of holding back these two groups of pawns here and here, in case the king wants to take shelter behind them. In the endgame, we don't need to worry about that as much though, so I've added a second pawn table to the code for the endgame, and let's just quickly set up some scores here. I'll give both the second and third rank a score of 10, because from a pawn's perspective they're the same distance from the end of the board, and then we can just increase the score for each subsequent rank. Okay, I'll now employ my highly sophisticated system of copying the string of values this little editor prints out, and then pasting that into the code. Alright, testing this, we've ended up with a small improvement of dubious significance, 365 wins to 353 losses. I'd be curious to know the probability that the new version is actually better than the old version based on this score, so if there are any statisticians watching, please let me know how to calculate that. Anyway, against version 1, it actually does seem to have helped a fair bit, taking us up to 670 wins to 142 losses, so that's nice to see at least. Alright, so with this table we're encouraging all pawns to move up the board in the endgame, but certain pawns are going to have a better chance of becoming queens than others. For example, this white pawn on the left here is blocked by the black pawn in front of it, so it won't be able to make it through on its own. Then this pawn in the middle does have a clear path ahead of it, but it's probably going to be captured along the way. And finally, this pawn over here is known as a passed pawn, because there are no enemy pawns that can block or capture it on its path to queendom. Age-old chess wisdom tells us passed pawns must be pushed, so I reckon we should give our bot a bonus for doing the same. But first, we need an efficient way of actually detecting these passed pawns, and I'd like to try do that using bitboards. So a bitboard is really just a single number that represents some aspect of the current position. For example, the number 65,280 would represent the locations of all the white pawns in this position. That'll make a lot more sense if we look at the number the way the computer sees it though, which is to say as a 64-bit binary number, in this case made up of 48 zeros, followed by 8 ones, and finally another 8 zeros. So in the code we can represent a bitboard as a U-long, which is just a 64-bit integer, and I'll actually make an array of these so that we can have bitboards for all the different types of pieces if we want. Now there are a bunch of different operations we can do with binary numbers. For example, the bitwise OR operation of A and B gives us a binary value with ones in the places where either A or B is set to 1. Then there's the AND operation, which gives us this, with ones in places where both A and B are set to 1. We also have the exclusive OR operation, which gives us this, with ones in places where either A is set to 1 or B is set to 1, but not both. Another useful tool we have are these left and right shift operators. So for example, if we take the value 1 and shift it 4 bits left, we get, well, exactly what you'd expect. So in the code, when we're loading in all the pieces for the starting position, we can look up the bitboard that corresponds to the current piece type, and do a bitwise OR operation on its current value, with the value 1 shifted over by the index of the square that piece is on, and that will set up all our bitboards. Of course, we also need to update them whenever a piece is moved, so over here we can just look up the bitboard for the type of piece we're moving, and use the exclusive OR operation this time to toggle the bits, so that the starting square gets set to 0, and the target square gets set to 1. Also, if this move captured a piece, we'll need to make sure that on the bitboard of the captured piece type, the target square is toggled to 0. I think that should work, but let's try it out to make sure. So I'll move this pawn up, and we can see the start square was toggled off and the target square toggled on. Let's also make sure that captures are working, so I'll let the knight snack on this pawn, and it has been removed from the bitboard. So this seems to be working well, although I just realized something actually. There's that pesky en passant move of course, always making my life just a little bit more difficult. Alright, I've been working on this for a while, and I think I've covered all of the edge cases. We do only need the pawn bitboards at the moment, but I got a little carried away and created this test interface here, so we can easily flip through the bitboards for all the different pieces and make sure they're working. Let's test that en passant capture first, so I'll set up a position quickly, and that's looking good. Another edge case is castling, because of course when the king moves we need to update not just its bitboard, but the rook's bitboard as well. And then finally, if a pawn promotes to a queen for example, then that promotion square needs to be added to the queen's bitboard and removed from the pawn's bitboard. We can also do things like have one really long line of code that ORs together all the bitboards of the white pieces for example, and that will give us a single bitboard telling us the location of every white piece, which could maybe be useful in the future. I don't know, I'm just messing around a bit here. To be clear though, this bitboard can't tell us what type of piece is on each square, which is why we need multiple bitboards to fully represent the position. This actually reminds me of a really great video by Tom7 where he creates all sorts of strange chess bots, one of which is piece blind, meaning it just gets 2 bitboards, one for the white pieces and one for the black pieces, and has to try figure out what to do from there. Anyway, if you haven't already left to watch that far more entertaining video, let's finally get to work on the passed pawn detection we wanted to do. So to tell if this is a passed pawn for instance, we need to look at these squares in front of it and see if there are any enemy pawns there. So let's try calculate a bit mask that covers this region. As a starting point, let's just write ulong.maxValue, and that'll give us a bitboard with all bits set to 1. Now we should be able to move this whole mask up the board by shifting all the bits 8 spaces over. That's not the direction I wanted, let me try that again. Okay, so that shifts everything 1 rank up, but we want to shift it 3 ranks in this case, since that's where the pawn is. So in the code, I already have a function for converting a square index to a rank index, and we can just multiply the 8 by that rank index plus 1. With that, we've managed to isolate the squares that lie ahead of the pawn, but we're only actually interested in the 3 files surrounding the pawn, where it can be blocked or captured by an enemy pawn. So let's start now by figuring out a mask for just a single file, like the A file here for example. I can't think of a clever way to do this, so I guess we'll just write it out by hand. Every 8th bit should be a 1, so 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3. Wait a second, there's a much less painful way to do this. Hexadecimal to the rescue. Alright, so here's our A file mask, and now we can just shift this around however we want. So if we calculate the file index for the given square, and then shift the A file mask by that many bits, here's what we get. Now we also want to include the 2 adjacent files, so for the file on the left that just means shifting 1 less, and on the right would be shifting 1 more. We don't want to go off the edge of the board though, because that'll wrap around weirdly, so let's do some quick clamping, and then we can just combine all 3 of those together into a triple file mask by ORing them together. Okay, so we're pretty much done, we just need to combine the 2 masks into one. So let's take that forward mask we calculated earlier, and return that, but ANDed with the triple file mask, so that only where both masks have their bits set to 1 will actually end up as 1. And after all this messing about, we've managed to create the passed pawn mask we wanted. Behind the scenes, I've also made a version for the black pawns going in the other direction. Okay, now to make use of all this, I've written a little function that evaluates passed pawns. So for each of our pawns on the board, we get the appropriate passed pawn mask, which has been pre-computed and stored in an array, and then we can simply AND that with the enemy pawn bitboard, and if that results in 0, it means that no enemy pawns are in the way, and so it is a passed pawn. Calculating it like this should be pretty efficient, since we don't need to loop over all the enemy pawns to find out if they're in the way, or anything like that. Anyway, we give each of these passed pawns a little bonus, and here are the bonus values I've chosen. So we have 90 if the pawn is 1 square from promoting, 60 if it's 2 squares from promoting, and so on. Now, these numbers have been pulled from thin air, so we should actually test and tweak them at some point to try figure out what values would actually work best. But for now, let's just run a little test match and see how it goes. Alright, we've ended up with 415 wins to 325 losses, which is a decent improvement, I'd say. And against version 1, we can see a rather modest improvement over last time with 687 wins to 137 losses. Now, a passed pawn is even more valuable if it's protected by another pawn, because obviously that raises its chances of surviving, so I've added some code for detecting and rewarding that, but mysteriously it's actually just made the program play a little bit worse. So let's try something else instead. In this position, white has 2 pawns that are isolated, which just means that there are no friendly pawns on the adjacent files that could ever support them, and in general these are a bit of a liability. We can very easily use our bitboards again to test for these isolated pawns, and apply a penalty depending on how many there are. Trying this out in a match, we get a modest 396 wins to 341 losses against the previous version, and against version 1, we're now up to 717 wins against 139 losses. Alright, so we've improved the evaluation function a tiny bit, but now that we have all these bitboards set up, I'd like to try using them to speed up our move generation using an interesting technique called magic bitboards. Beginning with the rook, I've so far just calculated a bitboard for each of the 64 starting squares, which simply tells us which squares the rook is able to reach from there. That's assuming the board is completely empty though. Of course, in reality, there's usually going to be some annoying pieces getting in the way. What we're aiming for here is to be able to take this bitboard of all the pieces that lie along the path of the rook, and use it as a key to look up what moves the rook is legally able to make. So essentially, we want to pre-compute the legal moves for every possible arrangement of blocking pieces, so that the move generator has less work to do at runtime. Now, technically, only the first piece that the rook encounters in each direction is actually blocking its path. Any pieces after that are irrelevant. So we could reduce the size of the lookup if we ignored those irrelevant pieces, since that's fewer configurations we need to store. Unfortunately, that would mean that whenever we want to look up the legal moves, we would have to have a loop running in every direction to find out where that first piece is that's blocking the path. But that's essentially how the move generation works at the moment, and is exactly what we're trying to avoid. So for the sake of speed, our lookup table is going to have to include lots of redundant piece arrangements. Anyway, that means that our task now is to figure out all the different possible arrangements of pieces along these 4 directions. The way I'm thinking about this is that we're essentially counting in binary. So for example, this would be 1 in binary, and we can see that up here. And so this would then be 2, this would be 3, 4, 5, 6, 7, and so on. But remember, we don't care about these squares, only about the squares where the rook can potentially move. So instead, we're going to say that only places where this movement mask is set to 1 are actually valid binary digits. So in that case, this would actually be 1, since that's the first valid place according to the movement mask. And so this would then be 2, this would be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so on, for all 16,384 different possibilities. So that leads us to a nice and easy way to implement this in code, which goes like this. We're given the movement mask, and we start by just creating a list of the indices of all the bits that are set to 1 in that mask. So for this mask, for example, that's index 4, index 12, index 20, and so on. Now, the total number of piece arrangements we're going to have is simply however many numbers can fit in that many bits, which is just 2 to the power of the number of bits. We're then going to count from 0 up to the total number of possible piece arrangements, and for each of them simply take the current number and shift each of its bits into the valid places. So just as an example, say we're on number 13, which in binary is 1101, all that the code does is shift those bits into these places here like this, and that represents this arrangement of pieces. So using that code, we can now browse through all the different patterns. So here we've landed on 4081, then here is 10,815, and here's where it ends. Okay, so what I've done now is just made a gigantic dictionary by looping over every square in the board, then generating all the arrangements of pieces that could block the rook's movement from that square, and finally just figuring out what legal moves the rook would have in each of those cases, and adding that information to the dictionary. So now, given the square the rook is on, and the current arrangement of blockers, we can just directly look up the bitboard of legal moves, and we can see that seems to be working. One important detail though is that these blockers are all being treated like enemy pieces, meaning the rook can move onto them to capture them. So we'll need to add a fix for friendly pieces later on. But anyway, since we're treating them like enemy pieces, that actually means that for the last square in each direction, it doesn't matter if there's a blocker there or not, the result will be the same regardless. And so we don't need to include those in the piece arrangements we're generating, which greatly reduces the size of our lookup table. Another important detail is that if I try place a blocker somewhere over here, for example, that's going to break everything because it's not a pattern that we included in the dictionary. So in the move generator, when we want to actually figure out what moves a rook is able to make from a certain square, we first combine the friendly pieces and enemy pieces into a single bitboard, and then AND that with this mask here. The mask looks like this. It's just the movement mask, but stopping one square short in each direction like we talked about. That will clear out any pieces from squares we don't care about, so that we end up with a valid key, which we can then use to look up the move bitboard from the dictionary. Finally, we just have to extract the squares that the rook can move to from that bitboard using this efficient little loop over here. Right now though, the rook is able to capture friendly pieces since we're treating all blockers as enemy pieces. So to get around that, we just need to take the bitboard of friendly pieces, then invert it, meaning the ones become zeros and the zeros become ones, and then use that to clear out the friendly occupied squares from the moves bitboard. Finally, a little bit more fiddling was required for handling things like pins and checks, but that was fairly easy to adapt from the old move generation code. So after all this work, I am excited to announce that the move generation is about 20% slower. For possibly the first time ever though, I think my code is not actually what's slowing things down, but rather the problem is the standard dictionary we're using. Obviously, it is designed to be fast, but it does also have to be general purpose, whereas we have a fixed set of data that we know ahead of time, and so we can create a lookup table optimized specifically for that data. So as an example, let's say we have the rook on this square here, and we also have some bitboard of blockers. From that, we'll want to generate a key, which is simply going to be the index into an array where the corresponding bitboard of pre-computed valid moves will be stored. Now, we can't just use the blocker's bitboard directly as the index because this number is huge, it's in the quadrillions, and it would be preferable if our lookup table could actually fit in the computer's memory. So the first thing we need to do is get our hands on a magic number. And what's magical about it is that it has a special property that we don't know how to calculate. We just have to try lots of different random numbers until we find one that works. Now, the special property is that when we multiply it with any of the possible blocker bitboards for the current starting square, the result will have all the important bits as far on the left as possible, with the bits further to the right being basically garbage. And I'll explain what I mean by that in a moment. But then we're going to shift everything over by some number of places, so that only these allegedly important bits remain, leaving us with a reasonably small number, which will be our index into the array. So this bitboard of moves we have here is going to be stored at index 131, and assuming that our magic number and our shift value were well chosen, then this index will be unique to this particular move bitboard. So when I talked about some of the bits being important and some being garbage, the garbage is just all the bits to the right that we can get rid of and still end up with a unique index. So as we've seen already, this move's bitboard will be stored at index 131. If we remove this blocker over here though, we get a different move bitboard, and that's going to be stored at index 127. Then this one will be stored at 895, this will be stored at 383, and so on. The point is just that the indices are unique, so that we don't end up overwriting one of the values in the lookup table with a different value. Of course, we can only guarantee this unique mapping because we know all of our data ahead of time, meaning we can literally just keep trying different magic numbers until we find one that works. However, finding a single magic number that works well for all 64 squares the rook could be on is not really possible, so we can simplify the task by just having a separate magic number and array for each of the 64 squares. Okay, so here's what running the brute force search for the magic numbers looks like. And you might notice I'm also generating magic numbers for a lookup table of bishop moves, which works exactly the same way as the rook. Now, we can see up here that the rook's lookup table is around 2 megabytes in size, but that will actually get smaller if we let this run for longer, because it will gradually stumble across better magic numbers that allow the data to be packed into smaller arrays. So after letting this run for a while, I simply saved the result to a file, and then pasted that into these arrays here. Then in the move generator, we can just quickly update our code here to calculate the lookup index using the appropriate magic number and shift value. And then this rook moves lookup is now a two-dimensional array instead of a dictionary. It'd probably be a good idea to flatten it into one dimension actually, but I'll worry about that another time. Just out of curiosity, I made a quick test to roughly measure the lookup speed of the dictionary we were using versus our custom approach. So accessing the dictionary is taking 762 milliseconds, and that's for many millions of lookups of course. And then doing the same number of lookups with our magic bitboard approach takes just 53 milliseconds. So that's nice to see. Alright, so all the sliding pieces are now using the magic bitboard approach, and by sliding pieces I mean the rooks, bishops, and queens. I have updated the pawn moves to use bitboards as well, although that just requires shifting some bits around, there's no magic lookups involved there. I haven't actually fully tested the pawn's move generation yet, but I'm pretty confident it works. Okay, never mind, apparently it's completely broken. It turns out what I missed is that pawns now have a new sneak attack where they can warp around the edge of the board and capture enemy pieces on the other side. A pretty cool feature if you ask me, makes more sense than en passant at least, but I will sadly have to remove it. Okay, so let's take a look at how much we've managed to actually improve the speed of the move generation in total. Running this full test suite originally took around 22 seconds to complete, and this old version used a list to store moves, so something I tried while I was testing all this Bitboard stuff is simply changing that to a fixed size array, initialized with the maximum number of legal moves in any position, which from a quick internet search appears to be this rather outlandish but technically possible position, where white has 218 legal moves. This change took running the test from 22 seconds down to 18. I then read some advice online about creating the move array using this stack alloc expression to avoid having the garbage collector poking its nose into our affairs. This does make things a little clunky because instead of simply asking for the moves and receiving them, nice and elegant, we now first have to allocate some memory on the stack and then give that to the move generator to store the moves in. The move generator will also then slice off the unused space, because on average there are about 31 legal moves in a chess position, not 218, so that ultimately we end up with just the actual moves. I don't really love this code, so I was a bit upset to see the test time go from 18 seconds down to around 15.5. I guess I'll just have to learn to live with it. Anyway, the final thing of course was implementing all that magic Bitboard stuff. And that has brought the time down again to around 9.5 seconds. Let's find out now if this faster move generation actually translates to playing any better. So against the previous version, it has scored 447 wins to 275 losses, which is not too bad. And against version 1, we're now getting 792 wins to 89 losses. Honestly, we probably could have made bigger improvements focusing all this time on other areas, but I feel like I learned quite a lot from the process, so I can't complain too much. Anyway, let's just try a few more quick things before we call it a day. One thing I've been tinkering with is the order that moves are searched in. For example, captures used to be ranked purely by the difference in the value of the pieces involved, so we'd consider capturing a queen with a pawn before we'd consider capturing a pawn with a queen, which makes sense. But now I am also using this bitboard of squares that the enemy attacks, which is created for detecting checks during move generation, to make a reasonable guess about whether the opponent can recapture the piece on the next move. And obviously if they're not able to, then that's generally preferable. Another thing I've been experimenting with here is a technique called killer moves. The idea is that inside of the search, whenever we encounter a move that's so good it causes us to reject the current line of the search, we record it as a killer move. And so for the rest of the search, even though we're not looking at the exact same position anymore, if it's still possible to play the killer move, we'll give it a high rank because there's a chance that it's still really good. Just as a slightly simplified example, in this position if white plays bishop takes bishop, black's best response is queen d1 checkmate. If instead white captures the bishop with the knight, black's best move is still checkmate. And if instead white captures the bishop with the queen, well, you get the picture. Queen d1 is a very good move in many variations of this position, so by giving it priority in the search, we can more quickly reject white's bad moves and hopefully find something that actually does defend against the threat. Okay, let's see how this does. So against the previous version, we have 477 wins to 221 losses. Pretty good. And against version 1, we're now scoring 851 wins to 51 losses. Another technique that ties into what we've been doing is something called late move reductions. The idea is that if our little move ordering scheme is working well, then the best move should be among the first few moves that we search, at least most of the time. So once we've finished with those first few moves, we're going to search the remaining moves at a shallower depth, because we assume they're probably not very good. However, if the evaluation turns out to be better than everything we've looked at so far, then we will have to search that move again at the full depth to get a more reliable evaluation. Hopefully though, those repeated searches will be infrequent enough to still speed things up overall, And hopefully that increased speed will outweigh the danger of the reduced search mistakenly thinking that a good move is bad just because it couldn't see far enough ahead. That's a lot of hoping, so let's see if it works out. Against the previous version, we're getting 397 wins to 238 losses, which I'm happy to see. And against version 1, we're now up to 873 wins to just 26 losses. Now, I've been idly watching some of these test games as they whiz past, and I happened to notice something a bit concerning. Every now and again, the program would be completely winning, but instead of making progress, it would just shuffle back and forth until the game ended in a draw. After a painful amount of debugging, I finally realized that this is probably because I'm only testing for repetitions against positions that have actually occurred in the game, whereas I should also include positions that occur inside of the search. So I've just made a crude little repetition table that handles that. I've then tested it against version 1 to see if that fixes the issue, and it at least seems to be helping a lot because we're now getting 898 wins to 27 losses, with the number of draws coming down from 101 to just 75. I would really like to beat the original version 100% of the time, but I'm going to leave that goal for the future because I'm beginning to see chess pieces in my dreams at this point. But first, I do want to get this little bot running on Lichess, so we can get an estimate of how good it is. To begin with, we need to convert our chess program, which is running inside of the Unity game engine, to a simple console application. I'm only really using Unity for rendering these cutting-edge graphics we have going here, so converting it is as simple as just taking this folder of core scripts and dragging it into a Visual Studio project, and then just deleting the occasional Unity engine.debug.log sprinkled throughout the files. Now, in this main function, we'll just keep looping until a quit command is received from the console, and simply forward any other console messages to the engine. I've then written an extremely crude and incomplete implementation of the Universal Chess Interface, which is a protocol for communicating with chess engines. So the communication between us and Lichess is going to go something like this. Lichess will say UCI, and we'll respond UCI OK. Lichess will then say UCI new game, followed by is ready, and we'll say ready OK. Then Lichess will tell us to set up the start position and give the go command, followed by the amount of time remaining for white and black in milliseconds. We'll then figure out what move we want to make and respond with this notation, simply the square we want to move from, followed by the square we want to move to. Once the opponent has responded, Lichess will send a new position command and give us a list of the moves played in the game so far. Then another go command with the updated times, to which we'll respond with the next move we want to make, and so on it goes. So let's now create a Lichess account to play on, and I think I'll simply call it the Coding Adventure Bot. I agree that I will at no time receive assistance from a chess computer. Okay, but what if I am a chess computer? Checkmate. Alright, I've generated an authorization token so that we can interact with the API, and I'll then just run a little command to tell it to upgrade our account to a bot account. If we visit the website now, we can see there's a cute little robot icon over here, and also a big bot label next to our name, so everyone knows that we're not human. Now, our little robot's actually not going to be talking to Lichess directly, but rather I'm going to use this super helpful Python repository to act as our go-between. So after downloading that, all we need to do is drag the compiled chess program into the engines folder, and then open the config file, and in there we just put our super secret access token, and specify the path to the chess engine. We can also customize all sorts of settings, such as whether our bot can play variants like anti-chess, atomic, and so on, which it sadly can't, although that might be fun to add at some point. Then, just for the first few days, I think I'll restrict the time controls to Bullet and Blitz games only, just so that it can hopefully get a chance to play lots of different opponents. That means that the slowest time control would be something like 5 minutes per side with a 4-second increment. I'll also turn off matches against other bots for the moment, because I'm most interested in seeing how it fares against humans. So if everything's been set up correctly, we should be able to fire it up by just launching the Lichess Bot Python script, and it looks like we're live. Now, our bot can't actually challenge humans, that'd probably be really annoying for them, so I'm going to post about it online, and hopefully some people will be in the mood to play. In the meantime, I'd like to try playing a game myself. Just for fun, I'm going to put our bot's evaluation of the current position up on the screen, along with the obviously far more accurate evaluation of Stockfish. Now, being able to see what Stockfish thinks the best move is might influence me a little, so I've engineered a high-tech solution, allowing you to see what it thinks, while keeping me in the dark. Okay, let's get this game started. We're playing 10 minutes per side, with no increment. I'm going to try being very aggressive, usually not a wise strategy against computers, but I think the weakest part of the engine is still how it evaluates king safety, which is to say, not at all. So I think it might make some sense to just throw all our pawns at the king, and hope something happens. In hindsight, I probably should have prioritized working on that aspect of the evaluation, but I got so sidetracked with all the Bitboard stuff, so I may need to subject you all to a chess part 3 in the future. Apologies in advance. Alright, I think I'm going to castle queenside here. I like that our rook lands opposite the queen, which should gain us some time. And then let's continue storming up with the pawns. What is this? So if we take the hanging knight, there's knight check, and then wherever we move the king is going to be checkmate. That's devious. So let's do this instead. Okay, knight takes. Aren't we winning a piece? Because if we take with the pawn, then the knight is pinned by the rook. Oh no, there's queen check here to get out of it. So queen takes instead, then if knight check here, we can take with the queen to protect the rook so we don't get mated. And in the case of the other check, we have bishop takes protecting the rook. So this should be fine. Okay, the queen's now attacking the other rook, so I'd like to move the bishop out of the way. It can only really go here, but then if the pawn attacks it, we'll have to retreat, and then knight check here is not going to be a good time. So I guess we need to move the rook instead. Alright, we need to rescue the rook again, and I assume the pawn's going to protect the knight, and also uncover an attack on our queen, so let's save her as well. And I think we better take this, because we're kind of running out of safe squares to even put the queen at this point. I am a little worried about this pawn here, but we can maybe pin it to the queen with the bishop and try hunt it down. Actually, don't do that because of this, so let's first take, then rook here. The pawn's going to go one forward, and then let's finally bring the bishop out. Okay, so black's attacking this pawn. I'm thinking maybe counter-attacking the bishop, and then if the rook defends, we can take this pawn because the bishop is... Well, I was going to say it's pinned, but actually there's check here, so scratch that. Maybe we just move the pawn one up then. I want to get back to charging these pawns up the board. I feel like our plans were derailed somewhat, but I think we can resume our attack. Hold on, I'm about to blunder this bishop check again. Okay, but now our attack is officially back on. This is suddenly starting to look really promising, actually. Black does have the annoying passed pawn, but the king is very exposed. Like, maybe we bring the bishop out here, and then we can start checking with the rook. Okay, I'm very tempted to bring the rook up here. There is queen check, king here, queen takes. What if we just keep running though, so king here? This seems pretty dangerous, but also kind of interesting. I'm gonna try it. Okay, that's an annoying move I failed to consider, stopping all of our checks. But what if queen here? If the pawn pushes, which feels like black's main threat, that is just mate in 2. So black would maybe need to respond by dropping the queen back. Something like this might be good then, but time's running low, we've got to go fast. Oh, I'd kind of forgotten about my king already, so pawn takes, queen check, king here, queen check. This is getting confusing. If we run up immediately with the king instead... No, there's no way we're surviving that. I think we have to take, queen check, now we have to go here. Oh, and that sequence removed the defender of our bishop. That's unfortunately very smart. Okay, but queen here threatens mate on g8, and if the queen takes the bishop, then we have mate on g7. but the rook can just take the bishop instead, so the queen defends g7. Oh no. We probably have to sacrifice the rook, although there is still bishop here threatening mate at least. Okay, we're gonna get checked a million times. Gonna have to come hide on the other side of the board. There goes the bishop, but let's see if we can give some checks at least. No, we're still the ones getting checked, of course. I'm really regretting my choices. Okay, good game, computer. The last time we played I felt like I still had an edge over the engine, but it definitely seems better than me now, which I have mixed feelings about. Anyway, we have had some activity in the console in the meanwhile, so it looks like someone took up the challenge online. Let's see if they've had any luck. Our bot played white in this first game, and it looks like it managed to build a slight advantage out of the opening, before losing it all by choosing the wrong direction to castle, according to Stockfish. Now we have an endgame that's slightly worse for white on account of black's control over the open file, and these weak double pawns, I guess, aren't helping either. Black slipped up a little here though in trying to put pressure on this pawn, because white can simply defend it, and now the rook is actually stuck in this little cubbyhole. The king urgently needs to come around to defend the rook from b3, but a few moves later and it's too late. Defending from this square is not going to work, because the bot is able to swing the rook around the back to chase the king away, leaving the rook undefended, and a few moves later we have checkmate. So thank you to the opponent for playing, and while we're waiting for some more games, I'm curious to see how the bot fares in a match against Stockfish itself. So I ran a match for 100 games, the result of which was, unsurprisingly, 0 wins, 0 draws, and 100 losses. Okay, we're getting crushed, so let's get our revenge by taking out the fish's queen. In a 100 game match with no queen, Stockfish was actually still able to win twice, which is a little scary. I'll give the queen back though, because maybe that was a little harsh, and for our last test, let's take away just a single rook instead. And the result this time is 31 wins, 8 draws, and 61 losses. So if there's one thing our little creation isn't lacking, it's room for improvement. Anyway, over the last few days it's played 270 games online, although only a fraction of those have been ranked games, so the ratings are still extremely uncertain. Right now though, it's just under 2300 at Blitz, which is roughly what I would have estimated, so I'm very curious to see if it remains in that region or changes dramatically. For anyone unfamiliar with Lichess ratings, a rough reference is that a total beginner is around 600, the average player is around 1500, and the best humans in the world are just above 3000. So I'll be keeping an eye on the Blitz rating, and as for Bullet, that is all the way up at 2600. My guess is that that's a bit higher than it deserves, because I have had the dubious pleasure of being obliterated in Bullet by players at that rating, and it felt a lot more hopeless playing against them than it does playing against the bot. For example, here's a Bullet game I played against it where I sacrificed a rook to destroy the pawn cover around its king. The bot is pretty pleased with its position at this point since it has an extra piece, but to human eyes, and fish eyes of course, white's vulnerable king is much more important than the extra rook busy doing absolutely nothing in the corner here. So I think that players better than me could probably exploit this king safety obliviousness to win a lot of games quite quickly. I, on the other hand, ended up missing a painfully obvious mate in 2 and lost the game. Of course, if the bot doesn't appreciate the safety of its own king, it also can't properly judge attacks on the enemy king. So here's an interesting game it played online, where back-to-back-to-back blunders left it with a very good position. But now, instead of realizing how this knight, in combination with the bishop and threats of the pawn promoting or the rook swooping in, have the white king in a serious pickle, it decided to just grab this pawn with the knight, and then wander off on some sort of side quest to harass the rook. White was then able to launch a swift counterattack against black's king, and ultimately trap it in a perpetual check to rescue the game. So I feel like this bullet rating might go down a bit with time, maybe to around 2450 is my prediction. Anyway, if you'd like to play the bot yourself, I'll leave a link to its page, and you can simply click the little swords to send a challenge, or the little TV to watch if anyone else is currently playing. In any case, I will leave you with a game between our coding adventure bot and Stockfish 15. Alright, thanks for watching, and until next time, cheers.